A computer mouse is an input device essential for interacting with your computer. It translates your hand movements into cursor movements on the screen, allowing you to navigate and control applications. Modern optical mice have evolved from older mechanical designs, using light and cameras instead of rolling balls to detect movement. In this video, we will dissect a modern optical mouse and explain how it works step by step, starting with its key internal components like the CMOS camera and LED. The result is smooth cursor control that lets you interact precisely with everything on your screen. When you move the mouse across a surface, the cursor on your computer screen mirrors that movement. The mouse detects its own motion and sends corresponding signals to the computer, resulting in intuitive and precise control. Let's dive inside the mouse to understand how this translation works. The optical mouse uses a CMOS camera sensor that captures thousands of images per second of the surface beneath it. An LED or laser light illuminates the surface, and the reflected light passes through the lens to the sensor. The mouse analyzes these images to detect movement patterns. Unlike older mechanical mice that used rolling balls, optical mice detect motion through image processing, providing more accurate and reliable control on various surfaces. The detected movement data is processed into XY coordinates and sent wirelessly or via USB to the computer, where it controls the cursor position. Modern computer mice rely on an optical sensor, essentially a tiny camera, paired with an LED or laser light source. This combination allows the mouse to track movement with incredible precision. The LED or laser light shines downward onto the surface beneath the mouse, illuminating any textures, imperfections, or dust particles. This light reflection creates a unique pattern that the optical sensor can detect. The optical sensor continuously captures rapid images of this illuminated surface. Each image shows the texture details, which change as the mouse moves. By comparing these images frame by frame, the mouse calculates how far and in which direction it has moved. In high-end models, this happens at an astonishing rate, up to 12,000 frames per second. This extreme speed ensures precise tracking even during fast movements, making the mouse incredibly responsive for gaming or detailed work. As the mouse moves, the optical sensor detects changes in the captured images. The CMOS camera takes rapid snapshots of the surface beneath the mouse. These images show slight differences as the mouse moves across the surface. Surface textures and imperfections create unique patterns that change with each frame. Sophisticated image processing algorithms analyze these changes to determine the direction and speed of the mouse's movement. The algorithms compare consecutive frames to calculate displacement. This displacement represents the straight line path from start to end, rather than the actual curved distance traveled. This displacement data is then converted into XY coordinates that the computer uses to move the cursor on screen. The XY coordinate data from the optical sensor is converted into digital signals using a process called quadrature encoding. This technique uses two channels, A and B, that produce pulse patterns to determine both the direction and speed of movement. This encoded data is then transmitted to the computer. For wired mice, it travels through a USB cable, providing a direct and reliable connection. Wireless mice use protocols like Bluetooth or 2.4 GHz radio frequency, offering freedom from cables but requiring battery power. Finally, the computer receives these digital signals and interprets them through its operating system. The quadrature data is decoded to determine cursor movement, allowing precise control on the screen. The computer mouse has three primary input mechanisms: the left-click button, right-click button, and scroll wheel. These components use either microswitches or optical encoders to detect user actions. Inside the mouse, these buttons connect to microswitches or optical encoders on the circuit board. A microswitch is a small mechanical switch that closes an electrical circuit when pressed, while optical encoders use light sensors to detect movement without physical contact. When you press a button, it generates an interrupt signal, an electrical pulse sent to the computer's operating system. The OS interprets this signal to perform specific actions, such as selecting an item with a left click or opening a context menu with a right click. The scroll wheel works similarly, using optical encoders that detect rotation through light sensors and slotted discs. As you roll the wheel, it generates interrupt signals that the OS translates into scrolling actions, allowing you to navigate through documents or web pages smoothly. In summary, the mouse's buttons and scroll wheel convert physical inputs into digital interrupt signals, which the operating system processes to control on-screen interactions like selection, menus, and scrolling. Wired mice transmit data directly to the computer via USB cable, providing a stable and reliable connection. Wireless mice, on the other hand, use radio frequencies like Bluetooth to communicate. This offers greater freedom of movement, but may introduce slight latency compared to wired connections. Wireless technology like Bluetooth 5.3 and 6.0 allows for low latency performance with great battery life. Modern computer mice feature adjustable DPI or dots per inch, which controls cursor sensitivity. Higher DPI allows precise control for tasks like graphic design, while lower DPI suits everyday use. Polling rate determines how often the mouse reports its position to the computer. Higher rates, like 1000 Hz, provide smoother, more responsive cursor movement, especially in gaming. Wireless mice now dominate the market, offering freedom from cords. Many feature charging docks for convenient power management. Ergonomic designs reduce wrist strain with angled shapes that support natural hand posture, ideal for extended use. AI integration enables predictive cursor paths, smoothing movement, and reducing fatigue in prolonged computer use. Sustainability focuses on recycled materials and modular designs, making mice easier to repair and more environmentally friendly. Future innovations include touchless and gesture-based controls, allowing intuitive interaction through mid-air movements and eliminating physical contact entirely.